Hello friends, welcome back. In Science 1 now we are going to learn chapter 4, that is electric spark. Now in this chapter we are going to learn many things about electric current, electricity. We are going to learn Ohm's law, Joule's law. We are going to learn what is current, what is potential difference, what are the circuits, what are the symbolic representation of the circuit. That means different types of symbol we are going to learn. Then we are going to learn what is the effects of resistances. So let us start this chapter. Now as I said that in this chapter we are going to learn many things about electricity. But what do you mean by electricity first? Or where it comes from? Generally we all know that we simply switch on the buttons and our electrical gadget starts working. Like your fan, like your tube lights, like your mixers, refrigerator, TVs, everything. But how this electricity is generated? First of all, the main power source is your hydroelectric. That means you must be knowing that water is accumulated in dams. It comes at very high speed. The generators are revolved and electricity is generated. So everywhere the generator is a main ingredient which generates the electricity. Now this generator is rotated by different means. The first is hydro, that is the water based. Second is thermal. Third is atomic. Then there are wind is used to rotate the generators. Like you must have seen the windmills. Then nowadays solar power is used. There are some non-conventional methods also, like the waves of the seas are generally used to generate the power or generate the electricity. Sea power or the waves. So in all these things, mainly the generator is involved, which creates or generates the electricity. Okay, but what this electricity means, where this electricity comes from or how it is generated, let us see that first. In the previous chapters we have learned that there are always free electrons in any metal. Okay, the electrons are loosely bounded. The force of attraction between nucleus and electrons is very less and electrons are free to move. Now these electrons can move around the conductor. Now consider this is a metallic wire. Let's say the copper wire. Now we know that there are atoms in any kind of metal. Okay, and in an atom there is a nucleus, and around the nucleus in an orbit there are electrons. Electrons are negatively charged particles. Now these electrons, there are some electrons which are very loosely bounded with the nucleus. So these electrons can move from one point or one end to another end of the metal wire or whatever the cross section is. Now these electrons are negatively charged particles. Okay. Now when these electrons move from, let us take only electrons. Now when these electrons can easily move from one end to another end freely inside the metal conductor. Okay. Now as I told you, these electrons are negatively charged particles. Those are the charged particles. This movement of the electron is called as electric current. That means the flow of electron, the flow of electrical charge is called as electric current. So the electric current is the amount of charge flowing through a particular cross-section area in unit time. Okay, it is current is amount of electrical charge flow through cross section in unit time. The perfect definitions, now again I remind you, the definitions must be as per the book, word to word. I am not writing here because it's meaningless to write it again. But you have to follow the definitions from the books only. What is the important here? What is the current? Is the amount of electrical charge through a particular cross-sectional area in unit time. So this is important here. But one thing is there. Copper wire is there. Free electrons are there. They are moving here and there in the wire. Okay. But do we say that current is flowing? No. You cannot say. I will give you one simple example. Okay. Suppose I have two pots. Those are connected with a tube. Okay. This is the water level. Right? We know that till these two pots are on the same level, this water level will also be same. Right? That means no other external unbalanced force is applied on this water. But what will happen if I press this water level? What will happen? This level will increase. Here I am applying some force on one side. On the other hand, suppose if this pot is on high level and this pot is on low level, what will happen? The water will immediately start flowing from higher pot to lower pot. This is a natural tendency to flow anything from high level to low level. Suppose this copper wire I am representing like this. Now here on the one side, I'll say one bulb is attached. We have seen that whenever that conductor is there, the free electrons are there, the free electrons are moving, they have the negative charge, but they are moving in any direction. Okay. Will this bulb glow? No. Why? Because these both ends are on the same level with respect to your current or electricity. So what I have to do? We know that electrons are there, the bulb should glow, but it will not. Because unless and until you give some movements to that electron, the bulb will not glow. And how will we give that movement? We will attach this wire to some electrical source. Let us say a battery. Battery has a positive and negative side. Once we are connecting here, we know that positive is always at a high level and negative is always on the lower level. Now what will happen? We know that the electrons are negatively charged particles. Whenever this difference is there, difference of level is there, immediately they start flowing to positive side. And now the circuit is said to be completed. Okay. In this case, from here out, electron cannot move out. Even from this side, electron cannot move out. Okay. So if the circuit is breaked here, if I break this circuit here, what will happen? even though there are positive and negative levels, still the current will not flow. Why? Because the circuit is braked, their path is braked. But as soon as I join this path, immediately the electron starts moving. This level is maintained, negative and positive levels are maintained, and electron starts flowing towards the positive end. So that will be the flow of current. So now it is clear, unless and until you give some potential difference, you create some potential difference, the electric current will not start flowing. Now I also told you that actually these electrons, negatively charged electrons, will flow towards the positive end. This is the actual flow of electron, but by convention in a circuit diagram we always show the flow of electron like this, from positive to negative. Now I told you that electrons are negatively charged particles. They have some electrical charge on it. I will denote that charge by Q. This current is flowing through some cross section for t time. That means for t seconds. So whenever an electric charge is flowing through the conductor for t seconds, the current I is calculated by Q upon T. So electrical charge upon time is equal to electric current. So when the SI unit for the electrical charge is coulomb. So when 1 coulomb of charge flows through the electrical circuit or any conductor for 1 second, then the current is said to be 1 ampere. Okay, you need not write AMP, you can simply write A. So the electrical current is said to be 1 ampere when 1 coulomb of charge flows through the conductor or the cross-sectional area for 1 second. Again remember, the SI unit for the charge is coulomb, the SI unit for the time is second, and SI unit for the current is ampere. Just to remind you, a charge on every electron is equal to 1.6. A charge on electron is 1.6 into 10 raised to minus 19 coulomb. This is just for your knowledge, or you may require this figure while solving your problems. Okay, now there are millions and billions of electrons in the circuit. Okay, we need not bother about it. So let us see the definition of 1 ampere. I already explained you here. Let us revise it again. When 1 coulomb of charge, when 1 coulomb of electric charge passes through a cross-sectional area of 1 unit in 1 second, then the amount of electric current flowing through the circuit is 1 ampere. So in this way, we can measure the electric current by means of amperes. But where this word ampere comes from? André Ampère, the French mathematician, he has done the great job or the great experiments in the electrical circuits. Because of his experiments, we are now able to measure the electric current. To pay homage to him or to pay respect to him, the electrical current, the unit of electrical current is named after him, that is ampere. A. Let us solve few examples on this. Before going to examples, I just want to remind you something. As I told you that electrical charges are of very small quantity. They are, even in current, is generally measured in milliamperes or microamperes. So before going to such examples, let me show you something. Suppose this is a unit scale. Okay, every jump is of 10 raised to 3 or 10 raised to minus 3. So if this is 1, here we have 10 raised to minus 3, 10 raised to minus 6, 10 raised to minus 9, 10 raised to minus 12. Or here, actually you don't need 10 raised to minus 12. Let us say 10 raised to 3, 10 raised to 6, and so on. So 10 raised to minus 3 is called as milli. 10 raised to minus 6 is called as micro. 10 raised to minus 9 is called as nano and pico. And here you must be knowing this. 10 raised to 3 is kilo. This is mega. 10 raised to 9 is giga, and 10 raised to 12 is tera. So when I say 1 into 10 raised to minus 3 ampere is same as 1 milliampere. 1 into 10 raised to 6, 10 raised to minus 6 amperes is equal to 1 microampere. And in this case you must be knowing, because you measure your memory of your mobile phones or your hard disks in this kilo, mega, giga, tera, 1 gigabyte, 2 gigabytes, 1 terabyte, something like that. In the current electricity, we are majorly concerned with milli, micro, nano and pico. Now let us solve few examples based on the current, time and charge. Okay, we know that I is equal to Q upon T. The one major mistakes students commit that they don't care about the units. Okay, suppose the electrical charge is given in coulombs, the time is given in seconds, then the electric current will be in amperes. But whenever the problems are given, they generally give time in minutes. Always remember that whenever you are calculating something, all these identities, all three identities must be in the same system. If you are using coulomb as a unit of electrical charge in SI system, then your time and your electric current must be in the SI system. Let us see one example. A current of 0.2 ampere is flowing through a bulb for 5 minutes. Find the charge that is flowing through the circuit. Very easy, very simple example. The first thing, whenever you are solving the examples in the physics, the first thing you have to remember that always note down first what is given. Though this example is very simple, but still we will go step by step. A current of 0.2 amperes. So I is equal to 0.2 ampere is flowing through a bulb for 5 minutes. T is equal to 5 minutes. Mind well, this is 5 minutes. Minutes is not a SI unit. SI unit is seconds. So you have to convert this. So 5 into 60, 300 seconds. And we have to find the charge that is flowing through the circuit. We have to find out the Q will be in coulombs. So I is equal to Q upon T. So Q is equal to IT, that is 0.2 into 300. The answer is 60 coulombs. So this is the answer. The only hitch in this is you have to convert these minutes into seconds. Let us see one more example. A charge of 420 coulomb. Okay, so here the charge is given 420 coulombs is flowing through a circuit for 10 minutes. So they are given time 10 minutes. So we have to convert into seconds, that is 10 into 60, that is 600 seconds. We have to find the current in the circuit. So we know that I is equal to Q upon T, that is 420 into 600. Calculate this. Pause your video and calculate. This is the simple arithmetics. So whatever current we'll get, that will be in amperes. Calculate this. The answer for this is 0.7 amperes. The examples are very simple and straightforward for the SSC level. Okay. Only thing you have to remember is all your units must be in the same system. You have to remember the formula for this. Okay. Let us go ahead.